In this section, we're going to look at the product and quotient rules for derivatives. These rules are two of the biggest ones we're going to use consistently for most functions. So in this section, we're going to identify when to use the product and quotient rules and then learn how to apply those rules to find derivatives. First, let's look at the product rule. This is going to be used when we have the multiplication of two different functions we want to find the derivative. So the rule is stated if f and g are differentiable functions, that means that we are able to find the derivatives and the derivatives exist at those points. The derivative of f times g is going to be the derivative of f times g plus f times the derivative of g. And we can write this in both notations, with the Leibniz notation or just with the prime notation. Usually the prime notation is how we're going to write this, as it's going to be a little bit easier to see. The most important thing to remember, and this is a big warning, and this is a mistake that a lot of students make, is that if you have fg prime, if you want to find the derivative, it is not just that you can take the derivative of the first times the derivative of the second. And this is where derivatives and limits start to diverge. As we had this rule for limits, you could just do the limit of one times the other, but it's not the same for derivatives. So, product rule, let's look at the first example, the derivative of 2 to the x times x to the ninth. We have our first function, we'll call f of x, that's our 2 to the x. And our second function, x to the ninth, is our g of x. So this derivative is going to be the derivative of the first, so the derivative of 2 to the x times the second plus the first times the derivative of the second. And writing it like this allows us to go step by step. So I am not done with this problem because I have these ddx's, and these are instructions to do more in the problem, in this case, to take the derivative. So if there are still instructions in the problem, that means there's more that we have to do. So first, let's take the derivative of 2 to the x. We learned that in the last video, that this is going to be natural log of 2 times 2 to the x. Then we multiply by x to the ninth, and we add 2 to the x times the derivative of x to the ninth, which is 9x to the eighth. So note that our first derivative here, we did the derivative of 2 to the x, natural log of 2, 2 to the x, and then we did the derivative of x to the ninth, 9x to the eighth, and everything else just kind of came along for the ride. So this is our answer. And again, note that it is not just going to be the derivative of the first times the derivative of the second. Now let's look at the quotient rule. So the quotient rule is used when we have the division of two different functions. So f divided by g. And this will be used when f and g are differentiable, and we also need that the bottom function, g, is not equal to 0, as we cannot divide by 0. That's still a rule, even though we can kind of deal with stuff with limits, we're not going to deal with the bottom being 0. So this rule is similar to the product rule with a couple differences. We have the derivative of the first times the second the derivative of the top times the bottom minus the top times the derivative of the bottom. Note that we have a minus sign here, which is different than the product rule, which we had plus. And then we divide by the bottom squared. So usually we're going to write this with the other notation, this prime notation. F over g prime, the derivative of f over g, is going to be f prime g minus fg prime over g squared. And I've heard this little saying that we have maybe high d low minus low d high, and that is backwards, sorry. Let's do that again, sorry. Low D high minus high D low square the bottom and away we go. And this is a silly little rhyme that helps us remember this formula. So low is G, D high is the derivative of the top, high is just F, and then D low is the derivative of the bottom. So it helps us to remember the order that I need the derivative of the top first. And then of course, square the bottom is going to be G squared. So let's see this in action with the similar kind of functions we did in the previous problem. The derivative of 2 to the x over x to the ninth. Here our top function is going to be f of x, and our bottom function, x to the ninth, is g of x. So we are going to have the derivative of the top times the bottom minus the top times the derivative of the bottom. And then we cannot forget to divide by the bottom squared. And just like with the product rule, we have two other derivatives to take care of in order to finish this out. We have to do the derivative of 2 to the x and the derivative of x to the ninth. So let's take care of each of those separately. The derivative of 2 to the x is going to be natural log of 2 times 2 to the x, and we have an x to the ninth left over from before. And then we have the derivative of x to the ninth is 9x to the eighth, and we divide by x to the ninth squared, which is x to the 18th. And note that we could do a bunch of simplification here. So for instance, we have an x to the ninth, or x to the eighth in every single term. So we could get rid of that. And that would allow us to write this as natural log of 2 to the x times x minus 9 times 2 to the x over x to the 10th. There's different ways you could write that, but I think that seems pretty simple to me. Another thing with the product and quotient rule we have to be weary of, not really weary of, it's useful, is that a lot of times you can think about the quotient rule as instead being an application of the product rule. And this is because division can often be thought of as multiplication. For example, instead of thinking of 7 divided by 4, we could write that as 7 times 1/4. Right? So 1 we think about as division, and the other we think about as multiplication. And it really is true that division is just a special case of multiplication. So instead of doing the quotient rule, let's do the product rule on this, where we think about this function as the derivative of 2 to the x times 1 over x to the ninth. And note that we can write that as 2 to the x times x to the negative ninth. So although technically we can do this every time, it's often better to write things using the quotient rule. It's going to be easier, but we can still do the product rule sometimes. So let's do the product rule on this. Our first function is 2 to the x. Our second function is x to the negative ninth. So the product rule says to take the derivative of the first function times the second function plus the first function times the derivative of the second function. So this derivative is going to be natural log of 2 times 2 to the x times x to the negative ninth plus 2 to the x, and the derivative of x to the negative ninth is going to be negative 9 x to the negative 10. And how is this the same as what we did before? Well, note that we have our minus sign there. That's going to be a minus instead of the plus. In fact, we could write this as natural log of 2, 2 to the x, over x to the ninth, plus, I'm sorry, I should say minus 2 to the x, 9 times 2 to the x, over x to the 10th. And this will be natural log of 2 times 2 to the x times x over x to the 10th. If you want to make it look like the other function, just rewrite x to the 9th, 1 over x to the 9th as x over x to the 10th. And then this is equal to what we found on the other page. So to verify that, let's go back to the other page. And this was the exact same thing we wrote down before. So these are exactly equal, but we can write it in a different way. And there's nothing wrong with writing our answer as so. We don't need to simplify it into a specific form. Lastly, I want to talk about the proof of the product rule. We're going to use some limits to do this, and note that the quotient rule is similar, but with some added difficulties. So we're just going to do the product rule right now. So if I want to find the derivative of fg, I'm going to write this as the limit as h approaches 0 of fg of x plus h minus fg of x all over h. And what that means is this is the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. And now we're going to do a weird algebra trick. So first of all, I'm just going to write down the previous step with a big space in between. So we have f of x plus h times g of x plus h, big space, f of x, g of x, all over h. And the weird step is I'm going to add and subtract the same thing. In this case, I am going to subtract f of x times g of x plus h. And then I can't just subtract something randomly, so I have to add it right back in. So to understand this step, maybe it makes sense to kind of go backwards, and if you would simplify this thing, you would cancel out those things I just wrote in red, and you would get the previous step back. It seems weird that we need to add something, but it's going to allow us to get the answer that we want. So now I'm going to group things. The first two terms, I'm going to pull out the common factor, and that is g of x plus h. And I am left with f of x plus h minus f of x. And the other term, I'm going to group the last two together. That's going to give me an f of x in common. And I'd be left with a g of x plus h minus g of x. And this is all over h. So lastly, I'm going to do some limit rules. I'm going to write this as the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. And each four of these limits are doable. The first one here, when you plug in 0 for h, we get g of x. Second one here is the limit definition of the derivative of f. Third one here, there's nothing to plug in for h, which means it's just a constant in terms of h. This is just equal to f of x. And then finally, we have the limit definition of the derivative for g, so g prime. And note that we could write that as f prime g plus fg prime. If we color code everything, this is f prime g plus f g prime. So this product rule is proven here. It's a kind of a weird limit proof. Remember that you are not responsible for replicating this proof. It's just good to kind of see where these things come from, know that they're not magic, and there's a reason why we have a more complicated product rule than we may think at the very beginning. The quotient rule is similar, and in fact, we kind of deal with everything as a product rule, so we're not going to show that one. In the next video, we'll go over a bunch of practice problems with product rule and quotient rule to get more familiar with them.